iron atoms and smash it together, you fuse them together, that will take energy away from it. It's not going to produce any energy. So you need to give it energy to try to fuse them. If you do that, then you're not creating anything that can act against the gravity. So gravity wins. The whole star is going to collapse very quickly in a fraction of a second because there's no energy that generated that prevents that collapse. So you're going to have what is called a supernova, a core collapse supernova. There are two kind of main processes involved during the core collapse supernova. The first one is the collapse and the transformation of the core into a compact object. I'll talk about that. And the second one is the explosion, so when you'll really see the supernova going off. Let's talk first about what's happening in the core. Wow, this is bright. So, you stop fusing, everything collapses very rapidly. What happens in the core is that all your iron atoms, the density will increase so much that they will be very much compressed, and then they will break apart into fundamental particles, electrons and protons. The whole thing continues to collapse, and then the densities get higher and higher, meaning that the electrons and the protons get closer and closer together. At some point, they'll be so tightly packed that they will actually fuse together. So electrons and protons will combine and form a neutron. So now you don't have these protons and electrons around, you have neutrons, and by doing that transformation, you also generate a lot of energy. So in a fraction of a second, you convert everything, almost, into neutrons, and by doing so, you create a lot of energy. You keep compressing them, the thing continues to collapse, and at some point, you will just hit a wall. You can't compress them anymore. They're as tightly packed as they can be. So collapse of the core stops there. The whole star continues to fall on the core, but the core stops there. It's compact, not moving. Then that gives rise to the explosion, so the second part. So basically, everything was falling onto it, and in a fraction of a second, you converted all that material into neutrons, and you generated a lot of energy. And what will happen is, as the material falls into the core, you have all this energy that will come and push all that material. This is a bit... Okay. Hopefully that'll be better. Okay. Sorry. Okay. Yes, so you have all this matter coming in, and then all the energy that you generated will be pushed, will push all the material that was falling in, and then you have material ejected at super high velocities. Lots of light is also released. It's very beautiful, like this. This is one very classic supernova remnant. It's called Cassiopeia A. Probably the most famous one is this one. Have you seen that before? It's called the Crab Nebula. So that was observed as a supernova in the sky by Chinese astronomers like 1,000 years ago. And now with our modern instrument, we can look at the Crab Nebula at different wavelengths, so different kind of light. So like X-rays and radio and optical. And then by doing so, you get a lot of different informations. Like in the purple, like it's coming. Here, purple is really interesting. That's X-rays. If we just stop and look a bit at the X-rays, on the left, you have Chandra data. So Chandra is X-ray telescope in space. You see something very cool. Here it's the same thing, but in the optical. What you can see in the X-ray is that there's a very tiny object here, very bright. There's some kind of jets coming out of it, and there's a torus around it. This dot here is, in fact, the core that kind of survived the supernova. Stayed there, very hot, and basically that core, which is mostly made of neutrons, we call them neutron stars. They're not stars, they're like the core of dead stars, but made of neutron. Oh, neutron star, yeah, sure. We do all kind of silly things, silly naming in astro. So this is really what I want to talk about during this talk, like this little object here in the center, neutron stars. So neutron stars are like among the weirdest objects in the universe, like for many reasons. Here's three reasons. First one, their density. Neutron stars have the mass of about 1.5 sun. Because at first, like, that star was very massive, like maybe 20 times the mass of the sun. So the core was itself very massive. So more mass than the sun. And then you've compressed it during the pre-supernova, during the implosion. You've compressed that thing into a sphere that has a radius of about 10 kilometers. Tiny, tiny, tiny. If that means that such a large mass and such a small volume mean that the density is like crazy high. If you were to take a teaspoon of neutron star material, there would be as much mass in that teaspoon as if you were to combine the mass of like all human beings on Earth. Like that's a lot of mass in a tiny teaspoon. Also, because you've compressed so much mass in such a small volume, the gravity there is like insane. If you were to go and like land on the surface of a neutron star or like crash on the surface of a neutron star, gravity will just crush you into a sheet that is about a few atoms in thickness. So, you know, billions of times smaller than a millimeter. That would be a very violent way to die. Don't go close to a neutron star. Second thing where they're really cool is that some of them rotates like super duper fast. They can rotate like a couple hundreds of times a second. That means that you have something that, you know, is like a bit smaller than the island of Montreal, and you spin it as fast as like your kitchen blender. Again, just that picture is like very violent. And finally, the last thing, one of the other things why they are so weird is that they have the strongest magnetic field that we have observed in the universe. These magnetic fields are like billions of times stronger than the strongest magnetic field that we've created in lab here on Earth. So that's a lot. Magnetars, they are the beast. Magnetars are a kind of neutron stars that have magnetic field that are thousands to millions of times bigger than a typical neutron stars. So that's like billions and then millions. That's like a lot of zeros. Yeah, so again, these are just like monsters. Yeah, okay, no, something I gotta say. In the 1930s, there was two guys, Bade and Zwicky. They predicted the existence of neutron stars not long after the neutron was discovered. They were like, oh, neutron exists, neutron stars. They predicted their existence when people were studying supernovae. But you know, how do you go about finding an object that is like about 20 kilometers in diameter, somewhere thousands of light years away from us? That was not trivial. So that was 1930s. A couple of years later, in the 1960s, exactly 50 years ago, there was this young astronomer, Jocelyn Bell Burnell. She was studying in England. She was doing her PhD at Cambridge, and she was building this radio telescope, and then she was using it to study the light, the radio light coming from quasars, which are a very distant, very bright object far away in the universe. And she was studying how the light propagated through space to us. And then one day so basically the way the telescope operated, it was just basically staring at the above sky. So as the Earth rotates, then the sky above us moves. We're moving, the sky doesn't move. But apparently the apparent sky moves above head, and then the telescope just sees sky above head. And it was using a mechanical chart recorder. So you have a needle, basically, that records the intensity, the radio intensity coming from the telescope. And then when you have a signal, then the needle, the pen, will react to that. So one day, she saw something kind of weird in their data. Here, that little chirp there, this is interference, so that's man-made, basically, that's terrestrial signal. And then she thought that this signal is clearly looking different than from this signal. So that was visible for a couple of minutes, basically. So what she did, she decided that the day after, same time, so same sky position, she would go back to the telescope, but then reduce the recording speed of the chart recorder, so you will have a better time resolution on the signal. This is what she saw. Every 1.3373 and some numbers, she saw these little pulsations. So actually, the curve is going down, but that means that it was recording a signal, basically. So she saw this very regular signal, this pulse that repeated itself every 1.3373 and some numbers. Very, very regular, very precise pulsations. Could have been interference, man-made interference. We're pretty good at doing like things that go beep very regularly. But then it was coming from, it looks like it was coming from that specific location. The sky was visible for only a couple minutes, same time of the day. So what they did is they went to another telescope somewhere else in England. Look at the same position. They don't have the same interference there than they had at Cambridge. So if that site saw the signal, that means that it's really coming from space. It's not like locally created by man. And sure enough, that other location saw the same signal, same pulsation. Back then in the 60s, like, we didn't know things that go just perfectly, perfect pulsation like this. So rapid too, like a star usually takes like days to rotate, so where could that come from? Sure, they call that signal little green men. Why not maybe some aliens trying to send us some very cool signals? Eventually, not long after that, they're starting to see more of these coming from elsewhere in the galaxy at different repeat frequency. So they were not getting the signals at like every 1.3373 and something number. So that kind of, killed the little green man theory. How could two, like, many civilization, like, all send us information to us at different frequencies? Like, what? No. So they decided instead to call these pulsars for pulsating stars. Didn't know quite what they were, but pulsars. Eventually, a very cool thing. They went back to the crab, and then they saw a pulsar right there, different spin frequency. It was a different repeat frequency. The pulsar in the crab repeated 30 times in 1 second. So then the connection was kind of clear. We expected there to be a neutron star there. Back then, we didn't have like that cool of an image. It was, it was not that clear that there was a central source there. X-ray telescopes were not around there at this time. So, we expect there to be a neutron star. We see a pulsar there. Pulsars are neutron stars. So that kind of made that connection. That was like huge. Jocelyn's supervisor got a Nobel Prize for discovery. Good job. But back then, we did not expect to see radio pulsations coming from a neutron star. Like, what the hell is happening? Now we know that a neutron star, a little like the Earth, has a dipolar magnetic field. So we have like this big bubble, magnetic bubble around the Earth. Neutron star has the same thing, and they have these magnetic poles. So at the we kind of see a bit like this is an artist representation, by the way. We've never seen that. But we kind of see, these magnetic field lines, and at the poles, that's where we expect a radio jet to be formed and to be emitted in space. So that's kind of the idea where the radio light would come from. And then each time the star rotates, basically, if the alignment is right, you might see a pulse. So I'm going to go more in details to really understand that. So really to see a neutron star as being a pulsar, because all pulsars are neutron stars, but not all neutron stars are pulsars. So to see a neutron star as being a pulsar, you need many things basically to see a pulsar, but the two main important points is that you need the magnetic axis, so where the blue light, the radio jet comes from, you need that axis to be misaligned with the rotation axis. So say rotation axis is like above head, you're turning that way, you need the magnetic axis to be misaligned with that, so that when you turn, you can create that sort of lighthouse effect. So that's one thing you need. Otherwise, if the radio jet points in the same way, radio jets will always be in the same place, and then you won't see that pulsation, that lighthouse effect. And then, of course, you need that radio jet to, at some point, sweep across the Earth. So if the radio jet is never aligned to the line of sight, you'll never see it. So if the jet misses the Earth, you won't see the neutron star as being a pulsar. So that's really like that's what we kind of understand of how pulsars are neutron stars. Now, how do we go about finding the pulsars? We know that they emit pulsations in the radio. So what we do, we use huge telescopes, and then we stare at somewhere in the sky, and then we look for pulsations. This is like the most prolific radio telescope when it comes to finding pulsars. It's the Parkes telescope, it's in Australia, has a diameter of 64 meters. It's really big. It was constructed in the 60s, so it's been around for a couple of years. Found many, many pulsars because it spent a lot of time to try to find them. This is the Green Bank telescope. This one has 100-meter diameter, so much bigger than the Parkes telescope, which has 64 meters. Green Bank telescope in West Virginia, this is the largest telescope that you can move. So it's the largest steerable telescope. It's much newer. It was constructed, it finished construction in the early 2000s. Found some pulsars too, but last but not least, Arecibo. Arecibo is, you can't move that telescope. It's built in a natural depression left by a sinkhole. Has a diameter of 305 meters, so 3 times bigger than this one. If you want to use Arecibo to look at different places in the sky, it doesn't move. So how do you look and point places? You move the instruments here. So all the antenna and what actually takes the data is right here. For like more than 50 years, Arecibo was the biggest telescope in the world until July 2016, when the construction of the Chinese telescope FAST finished. FAST is now the largest telescope in the world. Has a diameter of 500 meters, so like considerably bigger than Arecibo. It's really huge, but right now it's not. It's semi-operational. I think it's not finalized, but this is private to China, so can't use that to do my research. So instead, I use just Arecibo. It's good enough, The good thing about Arecibo is that it's so big, like FAST, that you can see very, very faint radio signal. So you can see faint pulsars or pulsars that are like really far away in the galaxy. So that's really the cool thing about Arecibo. You might have seen it in some movies. For example, in the movie Contact, where Jodie Foster, she tries to find signals coming from aliens. So she's looking for LGM, but all she can find is like pulsars, and that's so sad. And it was kind of fun. Also in GoldenEye, one of the James Bond movie, at some point, Sean Bean dies. This guy always dies in the movies. So he dies by falling onto the dish, and then for some reason the instruments explode and then falls and then destroy the telescope. Like, that's horrible. Good thing that didn't happen, of course. But what did happen is Hurricane Maria last fall, so in September last year. That was pretty bad for the telescope. One of the instruments here, it just fell in the dish, broke a couple of panels, and then so much rain, it formed a lake at the bottom. They called it the Arecibo Lake. But even with that, it was still operational. But some repair had to be made, and they were not sure if they were going to do it because it was very expensive. So the question was raised, like, do we care? Do we just let it die? And good thing they decided not to. So they're repairing it, and it will stay alive for a little while. So it's good. I can continue to do my research. So what do we do with Arecibo to find pulsars? We look basically in these two regions. So that's like a truncated region. Why do we look there? That's by the way, that's our galaxy. That's the disk of the Milky Way. We look in that region because that's where all the stars are. So it's kind of likely that all the pulsars are there. Chances are that we'll find them around here. And why do we not look like there? It looks like there's a lot of stars in that area. Because Arecibo can see that. It's just too south. So these are the two regions that Arecibo can see in the disk. So that's where we look. So basically we point the telescope in that region so that the field of view of the telescope is very tiny in that big green region. So we just look at one of these points and then we stare for 5 minutes and then we move a bit, 5 minutes, and then we keep moving until hopefully one day we will have observed that full area. We haven't done that yet. But so far we have the project has discovered 200 pulsars, which is good, but we know about 3,000 pulsars, which is a lot, thanks to Parkes in Australia. And we expect there to be many, many more pulsars in the galaxy. So 3,000 is a pretty good number. Why do we keep looking if 3,000, can't you do science with these 3,000 pulsars? No, we keep looking because sometimes we find really, really cool stuff. For example, we found planets orbiting pulsars. That's actually that's how the first planet outside our solar system was found. When you find cool things like this, it's pretty cool. We also find pulsars, neutron stars that come in pairs, so they orbit each other, and we can see them dance together. That's kind of also very cool, and then you can do very cool science with these things. I'll talk more about this in a moment. And also, you can see some kind of old pulsars that at some point they just start stealing mass from a companion star that is orbiting the pulsar. And when it just starts to eat that second star and then just spins up and then start to rotate super rapidly. It's kind of cool. So this is kind of why we keep looking, because sometimes we find things that we did not expect to find. This is kind of why we study pulsars. And also, there's different kind of science that you can do with pulsars. There's many, many things you can do with pulsars. And tonight, I'm just going to talk briefly about 3 kind of studies that you can do with them. Really cool things. One of them, studying new physics. By studying neutron stars and pulsar, I'll be interchanging pulsars and neutron stars a lot. By studying neutron stars, you have somehow access to physics that we do not see in the labs here on Earth. We know that in neutron stars, the matter is compressed to a point that we cannot reproduce on labs. We do not know how to put 1.5 sun into a sphere that has 10 kilometers in diameter. 10 kilometers, yeah. So we do not know what the physics does, how the physics works in these conditions. Many people are working on this. It's a very active field of research. Since we can't see that in labs, what astrophysicists do is they make some calculations, lots of paper writing, and they also do simulations. So, what if, if that kind of physics happening, what you see? So that's basically how you study the interior of neutron stars. We've learned a couple of things. One of them is that neutron stars are probably kind of like the Earth. They have a layered structure. So, you have, you don't see it here, but neutron star would have like a very tiny atmosphere, so a couple of millimeter thick. It would be mostly not like your nitrogen oxygen atmosphere. It would be just like electrons and protons, plasma at the very top, and then you have like a crust, you have a sort of mantle, and then you have a core. There are very funky things, we think, that are happening, kind of the boundary between the crust, which is mostly made of protons and electrons, and everything that is below, which is basically a big soup of neutrons. So we think that there the physics is becoming really weird, and that the neutrons and the protons there in that region would go through some phase transformation. So the neutrons will actually change shape. Instead of like your typical neutron, backyard neutron that is spherical, then you will see something different. You will see something that looks like pastas. It's really a thing, like scientists call that nuclear pasta. We actually have one expert on nuclear pasta here at McGill. So your neutrons, instead of being spherical like anything else, any other fundamental particle, you will start seeing things that takes the shape of spaghettis and lasagnas, and then spaghetti and lasagnas will mix, and then you'll have some waffles, and it's really like a thing. It's still not, it's still a theory. We haven't seen that. We haven't been there and cut a piece and see. But that's one thing that comes out of the simulations a lot. How does that happen? Like, we don't quite know, but some scientists have seen some similarities between what comes out of the simulations and some like cell cytoplasm, the structure of some cells. Now, I'm not saying that there are like living cells in neutron stars. I'm just saying that basically there might be some kind of similarities in the physics that is at work in these systems. So maybe somehow we could have access to that kind of physics here on Earth. But we're still, now we're kind of on the guard and looking for, can we see these kind of things elsewhere in other systems? So, yeah, so that's one thing, nuclear pasta, like we haven't seen it, it's not confirmed, but it's there a lot, we see that a lot, but even the basic questions, like what happens if we eat up a neutron star, or if we dump matter on the neutron star, how does the internal pressure changes? That's one question that we can easily answer with material here on Earth, but up there, like we don't know. Maybe it expands, maybe not. There are many theories. There are many predictions. People saying, oh, if you raise the temperature, that's what's going to happen to the pressure, and that's what we call equation of states. Many equations of state there. We don't know if many are right or which ones are wrong. To know that, we need basically two things. We need mass measurements of neutron star and also measurements of their radius. So for maybe 1 or 2 dozens of neutron star, we got to know their mass because they were in binary. So we know quite precisely the mass of a few neutron star, but we have no idea about their radius. They're so tiny and they're so far away. What we want to know is like, is it like 10.1 or 12.2 kilometers? Like we need a precise number if we want to be able to rule out what physics might be happening there or not. This is nicer. This is a X-ray telescope. It is attached to the International Space Station. It was launched in July of last year. We have a couple of people. Mel is there, right? Mel works with that telescope. And one thing that it could do, basically this thing is devoted to neutron stars, observing neutron stars. And maybe, hopefully, we're hoping that one day it will be able to give us some measurement of radius of neutron stars. Mel, you can tell me if I'm lying or something. Okay, so that's one cool thing. That's one kind of science that you can do with pulsars. Another thing you can do is study extreme gravity. more precisely, Einstein's theory of general relativity. So Einstein contributed, obviously, a lot to science, and one of his important contribution was his development of his theory of general relativity. So basically, he had a new perspective on what was gravity. Before him, gravity was Newton's vision, which is basically gravity is an invisible force between two bodies that have mass. So it attracts two bodies that has mass. So for example, I have a mass, you have a mass, so we are gravitationally attracted to each other. That was the idea of gravity. Einstein saw gravity instead as one of the consequences, one of the effects of bending the fabric of space-time. So if you imagine space-time as being like a trampoline, and then you put like a bowling ball in the trampoline, then the trampoline will be curved. And then if you just throw a marble there, its motion, it will want to go towards the massive object. So it will be attracted to the massive object just because space-time is curved in such a way. So this is how Einstein saw gravity. And his theory came with an equation, and with that equation, if you play around with it, what you can do is you can basically predict the motion of an object in space-time and say, basically predict its trajectory. And another thing that came out of his theory is that basically a gravitational wave would be emitted if you accelerate a massive object in space-time. So that was his theory, but basically he did not really believe that observing gravitational wave would be a thing. So theory was there. It had been proven a couple of times to be like not bad, like doing pretty good. And then these two guys came along in the 60s, 70s. They were using Arecibo to look for pulsars. And one day they found one that was really cool. So the pulsar, instead of emitting really regular pulsations, you could see a variation, a systematic variation in the time of arrival of the pulses of the pulsar to Earth. So at some point the pulses would be closely spaced, and then sometime it would take longer to get pulse. And that could easily be associated to the motion of the pulsar in a binary system. So as the pulsar was moving towards you, then you would get the frequency at which you would get the pulse would be higher. So you will see more rapid pulses. And as it moves away from you, then the pulsations are more spaced. This is known as the Doppler effect. And basically they did some calculations. They could do some very precise calculations because you know that the pulsar is very regular in nature. You're just seeing variation in the time at which you're perceiving the pulse just because it's moving. But you can track it down really nicely in space. And with their calculations, basically, they concluded that the companion star that was orbiting the pulsar was orbiting, had to be another neutron star. Too massive to be a normal star and too compact to be a normal star. So that was pretty cool. So you have a pulsar and its companion, it's orbiting another neutron star in a very compact binary. Moreover, they could predict so well, they could track it down so well in space that they actually saw that the two neutron stars were actually getting closer together. So the orbit was like shrinking. Then they just tested GR, general relativity, and see if the equation, basically if they could recover the motion of the pulsar with GR, and there was like a perfect match. Moreover, GR predicted that the system will be, the two objects would be drawn closer together because they would emit gravitational wave, and they will get closer together by a certain rate. And that was exactly the rate at which they saw the two neutron stars getting together. So that was, actually you can do that, yeah. Forgot I had a video. It's a short video. Okay, maybe it's not going to work. Okay. Oh no, I don't want that. No. Don't go there. It's okay. Basically, they're just moving around. So the other neutron star, we're just not seeing it as a pulsar. Maybe just because the radio jet was not aligned with us, so we wouldn't see it pulsate. But yeah, so GR predicted perfectly the motion of the pulsar, and also they saw the consequence of emitting gravitational waves. So that was the first kind of indirect detection. It's not a detection, but oh, that's sorry, it's kind of chaotic tonight. Oh wow. Okay. Wait. Nice. Okay. Should I do it again? No. Yeah, so that was indirect detection of gravitational wave. That was very exciting. They got a Nobel Prize for it. That was really fun. And I guess most importantly, it motivated other scientists to just keep going and build actually a gravitational wave detector so that they could directly detect gravitational waves. Because Olsen Taylor, they just saw a consequence of them being emitted. So, the goal was to see them for real. So, Einstein, when he made his equation, his theory, he wasn't even sure that gravitational wave was a thing. I think he changed his mind a couple of times, like, yes, because no, it's not a thing. But for sure, he did not expect people to be able to detect them. They would be just tiny ripples in the space-time and like too weak to be detectable. But it turns out that humans are pretty awesome. And 2 years ago, LIGO actually detected gravitational waves that were emitted by two black holes that merged somewhere far away, like a billion light years away from us in the universe. So they really detected the little ripples in space-time caused by the merger. And that was pretty cool. So that brings me to the last cool thing you can do with Pulsar, hopefully, which is detect gravitational waves. So with pulsars, neutron stars, you can see the neutron stars as being emitters of gravitational waves, which is what Olsen Taylor did. You can also LIGO. Last summer, they detected two neutron stars in a not too far galaxy. It was a galaxy 130 million of light years away, which is pretty far, but it's not like a billion light years away. So they saw two neutron stars merging in that galaxy, which was pretty crazy. So this is using neutron stars as emitters of gravitational waves. But what I want to focus on now is using them to detect gravitational waves that are emitted by something else far away in the universe, nothing to do with the pulsars themselves. So here the idea is to not use ground-based detectors, so not LIGO, but create a detector that will be so big that it's big like the galaxy. And then that detector will be based on pulsars that you will use as cosmic clocks. Because their pulsations are so precise, you can use them as clocks. But to do that, you need the best ones. So those are a bit more rare. Usually a pulsar is, it's regular, but there's some error associated to that. You need the best ones. And the idea is that if you have a bunch of them everywhere on the galaxy, and then you use them as clock, you look at them, you observe them, you look for correlated signatures, so little variations, tiny variations in these clocks that would be caused by a gravitational wave passing by in our galaxy. So if gravitational wave passes by, it kind of moves around the pulsar, and then you could see tiny variation in the pulsations. and then you try to make a big map. You get all the little tiny variation there and there, and you try to kind of say, oh, there was a gravitational wave passing by. This project is called Pulsar Timing Array. Lots of people working on this. Emmanuel here is working on that. It's been around for many years, and it will need a couple more years to see it succeed. But chances are good, right, Emmanuel? Yeah, we're on track. Okay, so now the question is, why that much trouble? Why building this thing while LIGO can do a good job already at detecting stuff that merge in the universe and produce gravitational waves? The answer is, we're not looking for your typical black hole merging. With the pulsar timing array, you would be sensitive to the largest black holes, so supermassive black holes, which have the mass of like 1 million suns that are located in the center of galaxy. You could actually track galaxies that are merging, and then you will see the gravitational wave emitted as the two supermassive black holes in the center of the galaxy get closer and then maybe eventually merge. So this is the kind of signals that the pulsar timing array would be looking for. This cannot be detected with LIGO. LIGO see like typical black holes and neutron stars. So why do we want to see this? First, come on, it's really cool. But also, it will tell us a lot about how the universe evolved. So how galaxies formed, they merged. So, if you see these things happening very far in the universe, that means it was when the universe was really early. So that tells us basically how the universe evolved to see the galaxy that we have right now. So that would be interesting for a lot of people. So just to recap, cool things you can do with pulsars. Among the cool things, you can do many more things. But yeah, tonight we talked about, nuclear pasta. Remember that, nuclear pasta, it's really cool. Understanding physics that it is not accessible here on Earth, that's cool. Studying extreme gravity, not gravity that you have access to in the solar system. Then you can test, is GR always right? Is general relativity always right? Is there a limit? Are we going to find a system someday that, where you need more than general relativity to explain what the pulsar is doing? So that's kind of cool. And also detecting gravitational wave, because that's a big thing now. Before, doing astronomy was looking at the light coming from the sky. And then sometimes also neutrinos, which is another way to look at the sky, but this is also very limited. But now we have this new window looking at gravitational waves, so this is a new way to understand physics that we didn't have access to before. So I think I'll stop here for tonight. Yeah, that's pretty much it. So I hope I convinced you that pulsars are cool. We've been studying them for 50 years. We've learned a lot of things, really awesome things. Many Nobel Prize with pulsars, they're really nice. But we still have big questions. So hopefully in the future we'll keep discovering really cool things, and I'll take questions. Yes? What's the difference between a neutron star and a black hole? We actually get light from a neutron star. So, we think that neutron stars and black holes could be like cousins. So if we think that, if a star is massive, when it dies in a supernova, if it was massive, but not enough massive, as the star dies, as the core contracts, it will form a neutron star. If there's too much mass in there, so if the neutron star has a mass of maybe 2 to 3 times the mass of the sun, that's one thing we still have to figure out. Then if you have more mass than that, then it will keep collapsing into a black hole. So we don't know much what is inside the event horizon of a black hole. You might learn more about this at Astronomy on Tap next week. Maybe not. But yeah, so they're kind of cousins. So if you keep compressing, if you collapse completely a neutron star, you will form a black hole, basically. So they're kind of cousins. But we see, we see light. The most important thing is that we see light coming from the neutron star and not from the black hole. It's in the back, yeah. Are there other astronomical objects that emit radio light other than pulsars? Yeah, totally. Even the sun is pretty bright in the radio. Stars emit in the radio. Even if you look at planets, if they have auroras, you can actually detect them in the radio. So many things, even on the Earth, we're so bright in the radio. It's disgusting when you do radio astronomy, actually. So yeah, no, there are many other things. Even supermassive black holes, they produce these jets. The active galactic nuclei, John works on them. Basically, yeah, so some supermassive black holes that are accreting stuff, they produce these like huge jets in the radio, and yes, those are super bright. So yeah, there are many things that emit in the radio, but the pulsars are the only one that we know that produce like very precise pulsations, and that's because of their rotation, basically. If you were to rotate like a super rapidly, like impossibly rapidly, supermassive black hole that has a jet, then maybe you could see it as like a pulsar, but no. Many things emit in the radio, yes. Oh. We'll just go here and then I go back up there, so keep your, yeah.
You may have mentioned this when the neutron star form, what happened to the protons and the electrons?
So,
Because all you have is the neutrons.
yeah. So when the neutron star forms, what happens to the protons and neutrons? So you've just like smashed them together. So we call that electron capture. Proton, electrons, if you just smash them, like there are nuclear forces that won't let you do this, but if you put enough force, then they will. And then you produce a neutron that way. So all the protons, if I have a neutron in my hand, within 12 minutes, it'll go back to being a proton and an electron. Because neutrons are not stable when they're just like that. But in neutron stars, they're so compact, they're so compressed that each time they want to break back into a proton and electron, they will just be smashed again into a neutron. But at the crust, so at the surface of the neutron star, we think that there's a layer of protons and electrons. So there the density will be not too bad. So they will, you could still have protons and electrons right there. Does that answer the questions? Yeah. Yes, there on the back. If there's other types of neutron stars? Well, there are these magnetars that are super weird. We don't really understand, how a neutron star becomes a magnetar, or how at some point they were magnetars and not normal neutron stars. So magnetars are the ones that have like crazy magnetic fields. And there's also what we call recycled pulsars. So at some point I had a slide, I talked about a pulsar that kind of ate its companion star and then started to spin up. That's another kind of neutron star. There are some that rotates, newly born. They rotate kind of rapidly and they are super bright, energetic. And then there's the old ones that came from that supernova that happened very long ago. And these tend to rotate really slowly. And so slowly, at some point, we think the radio emission would just stop, just like that. This is like, we have some kind of ways to kind of classify neutron stars as subtypes. Does that answer the question? Yeah. Yeah, sure. Good question. I hope we have an answer to that one day. We don't really know why they have that. That could be due to when they were formed during the supernova. Maybe something crazy happened. Maybe initially the star had a very large magnetic field, but again, everything there is kind of hand-wavy. We're having a very hard time to understand magnetars, and we have people studying them like very actively at McGill. Yeah. So why do neutron stars rotate so fast? That's a very good question. So we think they rotate really fast because during the supernova, during the implosion, when all the material falls onto the neutron star, the core, it will just give it lots of energy. And then not knowing what to do with all that energy or that momentum, then it will just start spinning. It's like, you give someone too much sugar, what it will do is just jump around everywhere. So that's kind of a bit like the idea with the neutron star. Just like at some point during the supernova, it got so much energy that it just started spinning really rapidly. It didn't know what to do with all that energy. And it's the same principle when I talked about, again, pulsar is that kind of steal matter from their companion star. This is stealing mass, so stealing matter is really stealing energy. So it just gained energy. What do I do with it? I'll just spin, because that's one thing I can do. So that's kind of, it's conservation of angular momentum. But yeah, sure. I don't know whose hand was up. Not that we know of. So is there a way to kind of replicate the energy and like use that energy from a neutron star? Not that we know of. Yeah, no. No, there are a couple neutron star people. I don't think there's, no. For now, we're just trying to understand everything there is to know about them. And then maybe, if we get more into that nuclear pasta thing, and then we kind of understand how to create that, how that is created, maybe there's a way to extract energy from that. But as of now, they're pretty inaccessible.
All right, let's end there. If you have any more questions, you can come on